Hi, I am Aditya and this is Heena, and we are presenting our homework 5, where we have built our own large language model in the style of GPT-2 for our final homework. And here we have adopted GPT-2 model architecture with a much lesser number of parameters. So we're using six layer of attention, six attention heads instead of the 12 that was used in the paper. And we are using a 6 layers of transformer encoder instead of the 12 that has been used in the original paper. So in this way, we are just trying to create a mini version of GPT and then see how it works on the pre-training and fine-tuning tasks that we have done before. And here for the pre-training, we're using an open web text of corpus, which was downloaded from Hugging Face datasets. And for summarization, we have selected two tasks. One is summarization, abstractive summarization, not extractive, and question answering. This has been done using the CNN Daily Mail and the Squad dataset respectively. And we have evaluated our model's performance using Blue and Rouge scores. And also I will be going through on a manual summarization on how each and every task has worked and the quality of the results.
Yeah. So to talk about the data loading strategy for this homework. So for pre-training, what we have done is that we our pre-training data loading strategy was inspired with the Karpathi's GitHub repo, where we have tokenized the articles with an end of text tag. And also in the data loading approach, we used the approach which was inspired by the homework for part one homework, where we have used the sliding through the concatenated article set, where we are creating windows of the length equivalent to the context size. And our whole process is measured in iterations rather than epochs, and all of this logs are you can view this in the 1B logs which have been attached in the report for both pre-training as well as fine-tuning. And coming to the data loading strategy for the fine-tuning part, what we have done is that the CNN Daily Mail Daily Mail dataset has long input sequences, and for that we have adopted a chunking and patting strategy. In this strategy, what we're doing is that for any article which is longer than 256 context size, we're splitting it into chunks of 256 tokens. And during prediction, what we're doing is that we are going to generate summaries for each of these chunks, and later these chunks are going to be sent to the model and then finally concatenated to produce the final summary. And the similar data loading strategy has been also adopted for the squad data set. And in this, we do not face this since squad data set does not have so many long sentences, long size sentence sizes as article size as the previous data set. We didn't face this issue much because the main length of the squad data set is 169 compared to the 868 tokens for the summarization articles. And we've used the same data loading strategy for both the tasks.
Yeah. So these were the some of the examples of the token generation performance after we have pre-trained our model. So the prompts was, "Hi, my name is," and the government is doing. And earlier samples in the earlier part of the pre-training, these were the kind of samples that we were getting, not very grammatically correct and not very much according to the topic. But after a good amount of training, the according to the prompt, we were getting grammatically correct sentences and also something very relevant to the topic. So the government is doing this, he said. Now let's look at the Trump agenda and so on. So from just gibberish, our model was able to learn good, comprehensible, grammatically correct sentences, even though it is a mini version of the GPT that we're using. And coming down to the model architecture, it was not an exact copy of what was presented in the Vaswani's paper. For example, for positional encoding, the paper uses a cosine and sine based mathematical concept to induce the positional encoding scheme. But here we're using a learned embedding scheme, wherein we're just using an nn.embedding layer and then adding it to our embedded tokens. So which also acts as a positional encoding. So, and then, yeah, of course, as I mentioned earlier, it is a more shorter, smaller form of the GPT-2 with just 6 heads and 6 layers of transformer encoders stuck up on top. And this is just a visual representation of the multi-head self-attention. So when we say multi-heads, we are going to use 6 attention heads, each responsible to bring out a different flavor of the input text that has been sent in. And this is the feed-forward block architecture, which immediately comes after the multi-head self-attention. So one transformer block basically looks like this. It takes in the input, which is sent through the learn portion embedding using an error embedding, and then goes to the multi-head self-attention, which looks like this, which has 6 attention heads, and then concatenated into the linear layers, and then it goes through this forward block, and then gets on the gets on an output. So over here, you can see that there are 2 residual connections, which was very similar to the Vashwani's paper that we done. So these were the model architecture, and for loss function, we just use cross entropy loss, wherein we send in t to t2 time steps of words, and then the prediction is going to be t+1 and t2 plus 1. So I am a boy is going to be the input, and I'm a boy end of token is going to be the output. So that's how we did the pre-training. And a similar strategy was also used for fine tuning. For fine tuning, the only difference was that we used extra tags called as get summary and question and answer, so that the model can understand what task it is currently supposed to do. And now moving on to the outputs results of some of the summaries that we've got. So over here, these were some of the results from the CNN mail data set. And you can see that the quality of the article and the topic that is pertaining to the highlights and the article is very much similar. Though we did not achieve good blue scores, we can see that the topic and the grammar of the sentences are very good. It's not pure gibberish. And over
even
here,
the predictions are like relevant to the input that we have given.
yes. So over here, you can see that when they're talking about Paul Walker and Fast and Furious, they keep talking about Fast and Furious. It's not hallucinating a lot, though it does hallucinate on minor details. The major details remain intact, and the quality of summarizations are also good. And as we can expect for smaller articles, for smaller size articles, the prediction, the summary was better because the lesser the number of chunks that we used and lesser concatenation that we had to do, it was able to understand the whole context, the whole article in one shot, and was able to generate better summaries in one thing. So this was the outputs for summaries. And for question answer, we faced similar kind of mixed results. And since over here grammar doesn't come into picture because the answer is going to be just 1 to 3 words maximum. So over here you can see that for the actual answer is highest social efficiency, but the prediction is the race of highest social efficiency, which is pretty close, but blue score still gives us 0.5. And yeah, most of the time it was the correct answer was not always correct. So here it's Alhambra, the main architects was coming out instead, but over here it's Peter Jennings and Peter Jennings way. It was a mix, but considering that this is a test data set after a lot of pre-training and that one a digital model of GPT-2, we were able to get good results. And it was a good learning experience for both of us to understand what actually happens under the hood of GPT. So thank you.
Yeah, thank you so much.